Hello everyone, and thank you for being here. My name is Adan Serna Reyes from Universidad Tecnológica del Norte de Aguascalientes, and today I'm going to present some recent results concerning the mathematical and numerical investigation of a fractional stochastic model for COVID-19 propagation. This is a collaborative work with researchers from Pakistan and Mexico. Here is the outline of the talk. First, we briefly discuss the background and motivation of the model. Then, we introduce the problem formulation and the main mathematical tools. After that, we present the analytical properties of the system and the numerical methodology. Finally, we conclude with the main results, simulation, and future perspectives. To begin with, let's look at why standard integer order models fall short when capturing epidemic waves like COVID-19. The motivation for this framework comes from two important aspects of epidemic dynamics. First, the historical accumulation of infections influences current transmission trends. This is a non-local feature that the standard derivatives are not designed to capture, since they only depend on the instantaneous state of the system. Second, the spread of a disease is subject to unpredictable events such as policy changes, behavioral shifts, and environmental variability. To account for this, we incorporate Brownian motion into each compartment of the model. By combining both approaches, the fractional derivative and the stochastic process, we obtain a framework that simultaneously captures memory effects and environmental randomness in the transmission dynamics. Before introducing the model, let me briefly mention the main mathematical tools we use. The Caputo fractional derivative is chosen because it effectively incorporates memory effects while preserving physically meaningful initial conditions, an important practical advantage over other fractional operators. For the numerical treatment, we employ a Grunwald-Letnikov type approximation, which allows to transform the fractional system into a discrete scheme that can be implemented computationally. These two tools form the analytical and numerical backbone of the work. Another important ingredient is the Mittag-Leffler function, which plays in fractional system a role analogous to that of the exponential function in classical differential equations. In particular, it appears naturally in the explicit solutions and bounds we derive from the model. We also employ a Lyapunov type inequality adapted to the fractional setting. This result is fundamental in the stability analysis, as it allows us to construct suitable Lyapunov functions and prove the global stability of both equilibrium points in the model. With these tools in mind, we can now present the proposed model. Here we introduce the proposed fractional SIR type model for COVID-19 dynamics. The system tracks the interaction between three compartments: susceptible, infected, and recovered individuals. The Caputo fractional operator of order theta appears on the left-hand side of each equation, incorporating the memory of the process into the dynamics. On the right-hand side, the nonlinear term describes the biological mechanisms of transmission, recovery, and immunity loss. The domain omega ensures that the total population remains bounded, and the state variables stay non-negative. The epidemiological interpretation of the main interaction terms is discussed in the next slide. Let me briefly comment on the three main interaction terms of the model. The transmission process is governed by the saturated incidence rate. This factor models a crowding or saturation effect. As the number of infected individuals grows, the rate of new infections slows down, reflecting behavioral adaptations such as social distancing. The second term groups all the way individuals leave the infected compartments. Disease-induced death at rate delta, recovery at rate beta, natural death at rate mu, and the immigration of infected individuals into the system at rate v. Finally, the recovered compartment includes loss of immunity at rate alpha, which allows individuals to return to the susceptible class. Next, we discuss some qualitative properties of the system together with the numerical methodology used in this work. The first property we establish is boundedness. From a biological standpoint, this guarantees that the total population cannot grow indefinitely, which is a necessary condition for the model to be physically meaningful. To prove this, we define the total population as the sum of the three states of the system. Under the reasonable assumption that the disease-induced death rate is at least as large as the immigration rate of infected individuals, we obtain a fractional differential inequality that governs the total population dynamics. Applying the Laplace transform to this inequality, we derive an explicit upper bound for the total population. The bound is expressed in terms of Mittag-Leffler functions, which is consistent with the fractional nature of the system. Using a standard identity for these functions, the bound simplifies to the total population being less than or equal to m. And m is the maximum between the initial population and A over mu. This confirms that the solution remains uniformly bounded inside the biological domain for all time. We also established the positivity of the solutions, which ensures biological feasibility. Specifically, we proved that if the initial conditions are non-negative, then all three compartments remain non-negative at all time. The proof is based on establishing lower bounds for each equation, and then applying the standard comparison theorem for fractional systems. The key observation is that the Mittag-Leffler function is positive for all theta between 0 and 1 in a real C, which guarantees that the lower bounds themselves are non-negative. We also established the mathematical well-posedness of the model by proving existence and uniqueness of solutions for any admissible initial conditions. The arguments proceeds by writing the system in vector form and verifying that the vector field satisfies a Lipschitz condition inside the domain omega. Since the nonlinear incidence term and all linear rates are bounded on this compact set, the Jacobian is uniformly bounded and the Lipschitz constant is finite. A fractional version of the Picard-Lindelof theorem then guarantees global existence and uniqueness of all time. The stability analysis is characterized through the basic reproduction number R0, which represents the average number of secondary infections produced in a fully susceptible population. The system always admits a disease-free equilibrium value when R0 is less than 1. This equilibrium is both locally and globally asymptotically stable, meaning the infection eventually disappears. When R0 is greater than 1, a unique endemic equilibrium state, E star, exists and is globally asymptotically stable under a mild condition on the saturation parameter gamma. In both cases, global stability is established using Lyapunov functions adapted to the fractional setting. Up to this point, the model is deterministic. However, epidemic dynamics are also influenced by random environmental fluctuations that cannot be captured by a deterministic framework alone. To account for this, We extend the model by incorporating stochastic perturbations into each compartment via independent Brownian motions B1, B2, and B3. The parameters sigma1, sigma2, and sigma3 measure the intensity of the environmental noise in each compartment. In this way, the model simultaneously captures memory effects through the Caputo operator and environmental randomness to the stochastic term. To analyze the stochastic system, we first rewrite the equations in an equivalent integral form by applying the Caputo operator on both sides. The resulting system is interpreted in Ito sense and takes the form of a Volterra-type fixed-point equation in the Banach space of square integrable continuous processes. Then, there are two important tools used throughout the analysis: the Ito isometry and Dup's maximal inequality. Working inside a closed ball B star in the solution space, we show that the fixed-point operator maps this ball into itself. The estimate for the S component is shown here. It has three contributions: the initial condition, the deterministic integral controlled by Cauchy-Schwarz, and the stochastic integral controlled by Dup's inequality and the Ito isometry. The condition theta greater than a half is required to keep the stochastic term finite. Analogous conditions hold for the other two components, and all are satisfiable by choosing rho sufficiently small. Finally, we verified that the operator is a contraction. Applying the same tools to the difference of two solutions, we obtain a contraction constant lambda that goes to zero as rho approaches zero from the right. This means we can always find a time horizon for which the contraction condition is satisfied. By the Banach fixed point theorem, there exists a unique Ft adapted solution almost surely, and the stochastic model is mathematically well posed. To approximate the fractional stochastic system numerically, we employ a Grunwald-Letnikov discretization combined with an Euler-Maruyama step for the stochastic terms. The scheme is written in a semi-implicit form to handle the nonlinear incidence term. The summation appearing in each equation reflects the non-local memory for the Caputo operator. Each new value of the solution depends on the entire previous history of the process. The stochastic increment is simulated as a Gaussian random variable. An important feature of the numerical scheme is that it preserves the positivity of expected values. The theorem states that if the initial conditions and parameters are non-negative, then the expected values of all three compartments remain non-negative at every time step. The proof follows by strong induction. Since the stochastic increments have zero conditional expectation, all stochastic terms vanish when we take them. The numerator of each recursive formula then contains only non-negative contributions by the inductive hypothesis, while the denominator is strictly positive. The argument is identical for all three compartments. We also prove that the numerical scheme preserves boundedness. We construct an auxiliary deterministic sequence n sub n that serves as an upper bound for the expected total population at each time step. The sequence satisfies a simple linear recurrence and convergence to a finite limit n star as n approaches infinity. This guarantees that the numerical population dynamics remain finite throughout the simulation, regardless of the step size or the number of iterations. The proof proceeds by induction as well. Taking conditional expectations in the scheme eliminates all stochastic terms. After summing all three expected equations, the incident terms cancel between S and I compartments. The recovery terms cancel between, I and R, and one of the assumptions removed the disease mortality surplus. The resulting inequality shows that the expected total population at the step n plus 1 is bounded by n sub n plus 1. Since the construction factor of the sequence is strictly less than 1, the bound converges geometrically to the finite fixed point n star. We now present some numerical simulations of the proposed model. The experiments were performed using the parameters shown in the table. The transmission rate changed across experiments. The remaining values are fixed and correspond to a biologically possible setting for COVID-19 dynamics. Here we present the numerical behavior near the disease-free equilibrium, with C equals to 0.3x0 and R0 less than 1. The infected population decays to 0, consistent with the analytical stability results, while the susceptible population settles, and the recovered compartment vanishes. Notice also that smaller values of theta produce slower convergence, reflecting stronger memory effects. We now observe the endemic equilibrium. The infected population persists with the stochastic oscillations driven by environmental noise. Given the high mortality rates in this parameter set, the dynamics reflect a highly lethal scenario, consistent with early pandemic conditions. Here, we analyze the stability regions in parameter space. The black curve is the threshold R0 equals 1, separating the two regimes. Green indicates where the disease-free equilibrium is stable. Blue, where the endemic equilibrium is stable. And red, where neither holds under the given conditions. This figure shows the dependence of R0 on the transmission rate C. The relationship is linear, with a critical threshold at C approximately equal to 0.456. Below this value, the system remains disease-free. Beyond it, sustained propagation becomes plausible. To conclude, let me summarize the main contributions of this work. We developed and analyzed a fractional stochastic SIR type model for COVID-19 dynamics that incorporates both memory effects and environmental randomness. On the theoretical side, we established existence, uniqueness, positivity, and boundedness of the solutions in both the deterministic and stochastic settings. We also constructed a Grunwald-Letnikov numerical scheme and formally proved that it preserves these biological properties at the discrete level. The numerical simulations confirm that the fractional order and the stochastic perturbations both have a measurable influence on the stability regions and the long-term behavior of the epidemic. As future work, we are interested in exploring alternative numerical methods such as non-standard finite difference schemes, comparing the Caputo operator with other fractional operators, and incorporating real epidemiological data and optimal control strategies into the framework. These are some of the main references related to the fractional and stochastic framework used in this study. Thank you very much for your attention.